The last time we were here, we were building a distributed database live on Twitch. And since then, we got incorporated, and it's great to be back. And this time, we're going to be debugging a distributed database live on Twitch. So welcome, everybody. Really nice to dust off the dust of Twitch Studio, update Twitch Studio, get things working again. And so cool to see everybody here again. We put this together really quickly today. It's spur of the moment, impromptu jazz. And the whole idea was we've had some people join our team, and we've all got different techniques for how we debug TigerBeetle. And we thought, well, it would be great to share this. You know, everybody's got a different way of debugging TigerBeetle. It's kind of an art. And so Rafael and Chaitanya were asking Alexi and DJ, like, can you show us some of the techniques that you've picked up on how you debug TigerBeetle? So we thought, well, let's do a call internally and just share this. And then we thought, well, hey, let's do this live on Twitch, and then everybody can see it too, and we can record it and put it on YouTube. And we're still going to figure out how to dual stream, but we're getting there. But then we can record it, and we've got it documented and just ways. So what you're going to see is a deterministic simulator, and then also some of the ways that we use it to fix, bugs in distributed consensus and storage in TigerBeetle. I'm not going to give the game away. First up, Chaitanya, you want to tell us what you're excited about today? So basically, just so everybody knows, this is a bug that we've never seen before. So it's the first time we see this bug, and Alexi is going to fix it, and maybe we'll help. We'll see. Chaitanya, over to you. How long do you think it's going to take?
From the very initial look that I am getting from the bug, okay, maybe I'll say an hour and a half. This bug. It's a very
Okay.
it's many minds put together. I hope we're able to get past it.
Okay, an hour and a
But
half times 4 engineers, so it's a pretty costly bug to fix. How many hours is that? 4 times an hour and a half. Okay, and you want to tell us about yourself? How long have you been on the team? What are you excited to learn?
of course.
Yeah.
So I joined TigerBeetle as an intern so this is my third week. So I finished 2 weeks yesterday, and I'm super excited learning everything about storage engines and diving into the LSM storage engine at TigerBeetle. But this is VSR is one thing that I haven't covered till now, especially in the TigerBeetle context. So I'm super excited to see how Alexi tackles this bug. So the reason I said 1.5 hours is because I'm probably going to be useless. I'm going to be learning. That's all my contribution is going to be, because I've never seen how a Whopper bug is debugged. But something that I'm excited about is how we would be able to reproduce the bug given the seed that Whopper produces. I'm excited to see that. And I think that would, yeah, I'm excited to see what that entails and how we can take it forward from there. Yeah. I'll hand it over to Rafael now. He can tell us a bit more about what he's excited about.
Of course. So, hello everybody. So yeah, I'm the TigerBeetle team since 6 months or so. So yeah, I'm very excited to learn about how we interpret it, of course, but also I'm really curious about how the operation entire process is done, how we put the hands dirt and debugging such a complex bug that we got here. So that's really amazing. So I'm excited to that. Okay.
Awesome. And Rafael, what's your bet? How long is it going to take?
Oh, I think that will be a short flight of 4.5 hours.
Okay, so maybe we're here till, is there a cutoff time? Like how long can we stream?
Nice.
Let's see. Yeah, so Alexi, thanks. This is all spur of the moment, no pressure. So we've never seen this bug before. We got it 7 hours today. Yeah, 7 hours ago. We don't know how bad it is, how easy it is. It's a consensus bug, and it's running a cluster, of tiger beetles and network faults and processes are crashing and it could be interesting stuff. Okay, maximum broadcast length is 48 hours. Thanks, comrade engineer. So the only problem is, I mean, I've got water. I don't have food or anything. So maybe we'll have to do some takeout or something and keep us going. Yeah, so let's see how long it takes. And honestly, we've never seen this bug before. So it's it's going to be, we're putting ourselves out there. Yeah, but Alexi, over to you. Tell us about Vopper.
Yeah, so first, let me tell a couple of words about myself. So I'm Alexei, also known as Smart Platform on GitHub. I'm with TigerBeetle, I think, since December last year, and yeah, basically doing stuff. I'm super excited. You might know me from my work on Rust programming language, but I kind of switched to Zix, switched to TigerBeetle, do distributed systems now. And I guess for this bug, yeah, I would concur with Chaitanya, and I would say an hour and a half, because we will spend some time covering the basics of a Whopper, how to run it, what's the output, how to graph logs, yada yada. And for the actual bug, I hope that this is actually an easy bug, because probably the code I added to our main branch yesterday is a culprit. And yeah, that's the case, kind of an hour and a half. That's something more complicated, then yeah, might take longer. Because it took me a week to add that bit of code, which presumably is a culprit here.
Okay.
Yeah.
We can do this. Yeah.
So yeah, let's start. So basically, this issue you see on the screen is what spurred this whole thing. Basically, this morning I was running Whopper with slightly bigger probabilities of failure to see if I can reproduce a bug I wanted to reproduce, by actually injecting the failure into the code. But turns out I caught a bug which is unrelated to the failure I was injected. And that means one of the two things. Either we have a genuine bug in our consensus on our hands, or otherwise the bug is in the Whopper, in the thing which checks the consensus. So let's start investigating. And as a first step, let's just try to reproduce this bug. And that's actually this is the awesome thing about TigerBeetle. So you see, in this issue, I pasted two bits of information. First, I specified the state of the code in the form of a commit hash, which I'm now checking out, and the small diff I need to apply to our simulator, this one, replica crash probability, blah, 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 blah. So let me find this replica crash probability. Okay, I think I need to remove two zeros here. Okay, so yeah, the first ingredient is the state of the code. The second ingredient is this seed. And I hopefully can paste it. And run it. And we should see a failure. And well, some login output. Let's see how reproducible our thing is, because the core thing you see in this issue, I didn't actually paste the stack trace, the actual failure, because this is not really necessary. It could be easily derived from a commit hash and from the seed, and this is because the whole our system is fully deterministic, and this it's really amazing that you can pin any super varied, super complicated bug to a single seed and easily reproduce it. And yeah, this actually fails with the failure I'm expected to see here. So okay, before we dive into actually debugging this stuff, let's get a quick overview of what Whopper actually is. And for example, let's actually try to, so here I pasted a specific seed. Let's actually try to find this seed by hand. So we are on that interesting command hash. And the basic way you run Whopper is you just run zig build simulator run. What this will do is that it will build the simulator in release safe mode. So with optimizations on, it will generate a seed at random, and it will run Whopper once with this given seed, which might either pass or fail. And yeah, because we are building in the release mode, it takes some time for LLVM to actually generate shell code. And the reason why we, by default, build this thing in release mode is because you are supposed to run Whopper in a loop, because most of the seeds would actually pass. And highly likely, the run we are currently seeing would also finish quickly with a success. So you want to run a bunch of those in a row until you actually hit a failure.
So Alexei, we built the binary once that's optimized, and then we run it again and again and again, and it's optimized so it speeds up the simulation time as well.
Yeah, exactly.
Yeah.
I'm wondering why it takes so much time to compile. It used to be faster. I wonder if Discord pushes this to efficiency core somehow. Okay, that's interesting.
We used to see this on the early ProtoBeetle benchmark, where if we were benchmarking TigerBeetle, a lot of the work was CPU, and if we had a video stream going, it would take a lot of that, or context switch.
Yeah. Okay, so basically we run this seed and it passed successfully. Probably we will talk about output in a bit, but let's show how to actually find an interesting seed which fails. So basically, you just run this. Yeah.
Alexei, can you take us through what is running behind the scenes? Is this just running one TigerBeetle process on your machine, or what is happening? How difficult is this?
Yeah. So that's actually kind of do things concurrently. I will run a bunch of simulate runs to find the seed, and at the same time, I will explain how this actually works under the hood. So I have this, I'm a super bad programmer. I don't know how to use shell. So I wrote my tiny program called and, which just runs the same command n times until it hits failure, which is perfect for this use case. So yeah, we are seeing that it tries to find something. So okay, so how this actually works? That is a simple program in simulator.zig file. So here is this main, and it is a single process, a single thread even, but it simulates the whole cluster. So let's actually go through main. So this is the main. Here are the parameters of our simulator. So just a bunch of constants which tells us how likely each particular failure is. And then we create a simulator. And the simulator isn't actually the interesting bit here. The interesting bit here is cluster. And this is where we create cluster. And I'm so amazed that go to definition actually works on Zig. It's ZigLS is great. Okay, cluster. So cluster is a simple Zig struct. It doesn't do any kind of networking, doesn't do any kind of IPC. It's just uses in-memory slice slice of replicas. And let's go back to main. The way this actually works is that we will tick the simulator like 50 million times, just like tick, 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 tick. Every tick is deterministic. There is no IO, no times happening. Like everything that goes is driven by this tick calls. And in this tick call, we will tick through the tick through the cluster, and in the cluster, we will tick through replicas, which will like fire all the timers inside replicas, logical timers, and we also like tick through the storages. And the storages is like mocked up testing storages, so everything is in memory and nothing is written to disk, and those storages would actually like inject deterministic delays and call the callbacks on the replica when like read is ready. So basically, replica tells to the storage, hey, I want to read this bit from disk. That goes into in-memory queue of vetted reads, and like 100 ticks later, this read is called back with like the data we have in our in-memory representation of the storage. That's why this is both very deterministic and also pretty fast. So let's get back to, okay. First, Joran, is there anything else you wanted me to cover here about how things work, how many processes are there?
I think you've got it. Did you mention we've got the clients there as well that we simulate, and the clients send in requests into the simulated environment, and then I guess the other thing, just to recap, is like Alexei said, we've got a lot of replicas in the cluster. Each replica has stable storage, but we simulate the stable storage with different corruption on the read and write path. We misdirect. Sometimes we just send the write IO to the wrong sector or the read to the wrong sector, although we simulate that differently just using corruption. We simulate different storage latencies, and then the replicas are all in process and they can send messages to each other over the network, but we simulate the network that they each have to do that, and we simulate the network latencies asymmetrically, different types of partitions. Sometimes we drop messages. Yeah, because actually, like, it's pretty interesting. TCP can have all these kinds of network faults. You know, you only get the TCP guarantees within a connection, but once you lose your TCP connection, if you do another one, you're basically back to UDP. All bets are off, you know, if a message was delivered previously or not. So we kind of model and simulate everything in the worst case as if we were doing UDP. Yeah, and that's it. Yeah, it's pretty cool there, that line in the event loop, Alexei, like a bit up where you see all the ticks being called, and you've got like replica clock.time.tick. So even the source of time for each machine is simulated. But what this means, I don't know if I'm giving the game away too soon, but we run the simulation in a while true loop. So normally we would tick time at 10 millisecond granularities. That's how we would, we would check our timeouts. Do we need to do something, or in the real world? But in our simulator, we just tick that in a while true loop. So we get like a 700 times speed up factor. So like, yeah, if like 3 seconds of simulation time is the equivalent of 39 minutes roughly on average of real world test time. So if you see like a 3-second simulation now, as we go and look at the output, that's actually giving you 700 times more real world events, interesting stuff happening. Yeah. Anything else, Alexei?
So
Any questions?
I have a question. So I'm still a little hazy about what exactly our seed refers to. Like, does it refer to snapshot of the configuration that caused the fault, that caused the bug, or is it a sequence of events that caused the bug? What exactly does that seed refer to?
Excellent question. So the seed is the seed for pseudo random number generator we used to determine
Okay.
the sequence of events. That's actually a fine interesting thing. So if you think about it, what we simulate is a system which reacts to a sequence of inputs. And like the actual our actual input is this like sequence of events, which is not necessarily compressible. So you could imagine a simulator which starts not with a seed, but with like a whole pseudo-random sequence. And that actually has interesting properties in that if you have a sequence of events, then you can intelligently like shrink it. Like you can like delete a single event and like see if it still triggers or false or not. For us, right now, we actually do something similar, something simpler. We just we use just a seed for random number generator and like expand this sequence of events from the seed. This means that we don't really have any fancy minimization here, which so far we kind of like didn't need to. Like, I mean, for all the bugs we had, it took us any time to debug any bug. If it turns out that this particular bug needs like infinite time to get to the bottom of it, then we will implement some interesting minimization.
Yep.
Does that answer your question?
Yeah, for the most part. One small follow-up.
Yeah.
So from what I understand, we give the random number generator our seed, and to my understanding, that is what determines the probability of what our fault injection is. Let's say we are injecting 10% storage fault on each replicas. Is that the extent of what the seed gives us, or does it give us even granular uh, sort of control over events? For example, when to inject the fault, when exactly the fault should be injected.
So not exactly. So the seed is just the seed for random number generator. Everything
Okay.
else kind of like flows from this PRNG,
Okay.
but how exactly are we using this RNG isn't encoded in the seed anyway. For that, we have a special thing, which is called cluster options, which is specifies like various kinds of probabilities, which are then fed into the RNG. So basically, if we look at the, let's actually just crush. So yeah, let's just look at the code for crushing the replica. So if our replica is up, we compute the crush probability from our options, and also kind of like here's like this funny thing. So we kind of like manually inflate particularly tricky cases. Like if a replica is actually writing something to this, we crush it with a higher probability because crushing a replica which tries to put stuff on it is probably more interesting. So anyway, we get this probability, then we ask our random number generator for like coin flip with this probability, and this is like determined by our seed. And then we crush replicas. So we don't have any kind of like fine-grained control over what happens, but we do have some interesting like manual tweaks to make the failures more interesting.
Sense. Thanks. Thank you.
Okay, perfect. So actually, like I have two items on my stack. One of those I actually forgot, but let me revisit the other one while I still remember it. So I want to show side by side the difference between the simulator and our actual main loop. So on the right, this thing is our actual production loop. And on the left, it is like what we do in the simulator. So first thing first is like there's like three lines of code which actually kind of like drive the whole thing. This is beautiful. I really love like this aspect of TigerBeetle that you look at me and you understand what is happening because like the heart is like so simple, so compressed. And the difference here is that we kind of like in the real setting we take the replica and then we let our IOU ring thing to run the callbacks for how long our ticks is set to, which is, I think, 10 milliseconds. And in our simulator, we just tick continuously. So there is no this like 10 milliseconds wait. It all goes like time, like basically the speed of time is bounded like by the speed of light and by the speed of like CPU processing. well, the speed of CPU processing is bound by the speed of light, so yeah, it's kind of like all checks out. Okay, perfect.
And maybe I can jump in here as well, because maybe people are wondering, how does this compare with Jepsen? You know, because Jepsen can also, you can take any database and Jepsen will, you know, mess with the network and crash processes and test that it, you know, the distributed database maintains strict serializability. There's two big differences. The first one is that Jepsen you run in real time because you run on a real binary, you know, so how long it takes, it takes longer. You know, if you want to catch a bug that takes a minute to catch, you have to run it for a minute. The second difference is that with Jepsen, if it takes a minute to catch the bug the first time, when you run it again, you might not catch it. Now you might need to wait an hour, or you might not catch it. So the reproducibility, you know, yeah. Whereas with the VAPA, with TigerBeetle Simulator, the code is all deterministic. So if you catch a bug, you'll catch it again. And it's quite nice, again, with the seed, you can just drop it in the chat. You know, like we could drop it in the Twitch chat here, and then everybody can go and run the VAPA on that commit hash. We could actually do that if we wanted to on stream, you know, and everybody can be reproducing this bug like right on their machine all around the world, which is quite cool. As a team, it works great. And then you can also speed up time so that you don't have to wait. If the bug is an hour-long bug, you can replay the bug locally with the simulator in like 3 seconds, 4 seconds. So you don't, for bugs that are hour-long bugs, you can debug them with iterations, you know, of like 3 to 4 seconds. Yeah, that's it.
Yeah. So as a bit of napkin map, you see in the code that we see it in the code. Yeah, you see it in the code that we run Whopper for 15 million ticks, and each tick is 10 milliseconds of real time, like your production database. So that would mean that like each run would take 500 seconds, so kind of like 10 minutes. 10 minutes for a run. And right now we like did like 64 runs like while we were speaking, which is like significantly faster. And the second bit is that, again, if we look at our original issue, like the trick here is that I changed the probabilities. I made crashes more probable. And while we were trying to reproduce this, I actually forgot to apply this dip. That's why we went through all the 64 reproduction attempts without finding a buggy seed. So let's do this again. And while we are doing this, let's like explain like this cryptic output of what is this. So this is a concise summary of the state of a cluster. Let's actually, can I quickly copy this?
Yeah.
But it doesn't. Okay. So this is a concise summary of the state of the cluster, which is printed by this log replica function inside cluster.zip. So like the TLDR is that this output is quite important, and it's normal to have no idea what it actually means. And to learn it, the best way is to go to the source and see what actually is being printed. But let me explain this. So first of all, cluster consists of replicas. And here we see a line for replica. And the very first number is an idea of a replica. So you see that we have like 2 entries for first replica, and then for the fourth replica, for the fifth replica, for the second, for the 0th, blah, 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 blah. And let's see what actually happens with replicas. So let's start with like this number. So 237G is a view number. And as you see, all the replicas are in the same view number. The next thing is commit number. So the lower number is what replica has locally committed. And these two entries are actually interesting. So you see that the commit number here is updated from 94 to 95. And that's exactly like why these logs are printed. So a replica committed, it's updated its commit mean, and that's why we do this print out. The second, the third column is the journal. So which prepares replica actually has in its journal. And again, for us, we do this thing where we commit iterations strictly in order, but we kind of like pipeline preparing them. So while one iteration is not yet committed, replicas might actually come to consensus on what a follow iteration should be. So that means that like just looking at the committed iteration on replica doesn't tell you what this replica has locally and what it has committed to for guaranteeing durability. And that's where kind of like this journal comes in. So it says that right now this replica has entries from the 50th iteration to the iteration 113. That's kind of like a whole bunch of iterations. And kind of like, okay, I realize that I need to like diagram this because it's actually pretty fun. So we have like this journal which contains like iterations. And because we want to okay, let's make it a short journal. Actually, I can put things over. Okay, so this is our journal. And because like, and then kind of like if you read consensus paper, it says like, hey, replicas have this like log and it like grows infinitely, and like from a mathematical point of sense, it makes sense. From a engineering point of sense, you kind of like don't have infinite amount of RAM, you don't have infinite amount of disk, you need to like compress this data. And especially if you write software like TigerBeetle, which doesn't use dynamic memory allocation, where all the resources are pre-allocated to the front, and you kind of like need to be very cognizant of what data goes to which memory. So we can't have like infinite log. That's why we have like a log of a fixed length, and every time this log deals with prepares, we actually go and compress it into a checkpoint. Then kind of like the log becomes empty. And like one complication when you need to keep in mind while you're working on TigerBeetle is that actually this is a simplifying picture, because actually our log is slightly longer than a checkpoint. So this is like a checkpoint worth of things, and this is like an extra gap which we need for compaction. So what actually happens is that you fill the whole log, and then you collapse the prefix of the log into a checkpoint, and then the end of the old log wrap becomes the beginning of the new log wrap. So yeah, kind of it's not super relevant for, I hope, this is not super relevant for what we are going to debug right now, but it's kind of like this is, at least this is like a big confusion point for me. I didn't understand how log corresponds to checkpoint. And like there is no direct correspondence because there is like extra operations on top of checkpoint.
So in other words, we do the checkpoint before we get to the end of the log, and then the point at which we do the checkpoint, that kind of becomes the start of the new log. So yeah, is that right?
Yeah. Okay. Next column. Next column tells us about the state of a journal. So again, like this tells us what replicas we should have in our journal, but like our journal is on disk, and kind of like disks can actually be faulty, this can nearly be something. So it might very well be the case that we expect the separation to be on this, but actually when we try to read it, we realize that, hey, there is a checksum mismatch, something got corrupted, and we don't actually have the separation. That's what is the meaning of this call. So I think the first number here is the number of dirty entries in the journal. That is, this is for something that we have in memory but haven't yet written to disk. So once we get a prepare from someone, we start writing to disk and we mark its corresponding journal entry is dirty. Once it is fully on disk, we clear this dirty bit. And the second number here is a faulty bit. That means that, hey, we don't have prepare in memory, we tried to read it from a journal, and we actually got a fault. The prepare is corrupted, so we need to repair it. Okay, the next one is, okay, actually, this I think you're going to help me, because I always I still confuse what is like journal and what is like write-ahead log. So I think one is for headers and one is for prepares.
They're actually the same. So in the code we call it journal, and we could even just call it write-ahead log or while. We used to always just call it journal, and then we started calling it write-ahead log. I don't know. Maybe we should go back to journal because it's a one syllable less, Alexi. But it's the same. So what we do, but conceptually, we think of it as one write-ahead log, but internally, our write-ahead log is actually two write-ahead logs. And the reason for that is in our QCon London talk, if you jump onto our TigerBeetle YouTube, anyone who's watching, if you're curious, TigerBeetle is like one of the few databases that actually we implement our logical write-ahead log with two physical write-ahead logs, which sounds really weird. Like why on earth would you want to have two write-ahead logs to give you one, logical write-ahead log? But the reason is so that we can handle all kinds of storage faults. So yeah, the write-ahead log, the journal manages what's on disk and what's in memory, but you have to remember that there's two things going on. So what we have in memory as well is we have this is what the journal manages in our Zig code is we have all the headers of the entries that are in our write-ahead log on disk. We keep a copy of them also in memory. And again, this is all for like storage fault recovery. So it's pretty interesting what TigerBeetle can recover from. But over to you, Alexi. The show must go on.
Compress this a bit. So we do split logs and we write prepares. So the actual like big like things with like actual transfers and headers separately. And I think one of the column tells us about the state of the headers, and another column tells us about the state of prepares. So that probably means that I didn't have to debug a bug in this area of the code because I don't really know. But anyway, kind of like the bottom line is that like this is like your first line of understanding what happens with Whopper, and this is all handled in this log replica. Oh, actually, I mean, like I've been talking about like boring numbers and whatever without actually kind of like explaining what's like this like I don't know like Space Invaders game going on here. So this actually is fun. This column is a concise summary of a role of a replica. So the / replica leaning forward is a primary replica, and you can actually see so. Kind of like that means that like if we are in view 237 and replica 0 is primary, then the number of replicas here should be a divisor of 237. I'm not sure what's like the divisor of this number, but anyway. So this is the primary. The replica, like the slash which links back, is a backup. We have like some amount of backups here. And the thing with just stand is a standby. So standby is a separate kind of a class of replicas which do not participate in the consensus. They just listen to the prepares, they apply prepares to their local disks, but we don't like provide extra redundancy in a sense that they don't participate in consensus. Why do we need like this standby replicas? Well, for like two reasons. Well, three reasons. Well, many reasons. But one reason is just to be able to run canary. So we want to add a replica to a cluster and let it actually like process transactions to check that it behaves in the same way, doesn't crashes, it doesn't diverges in terms of state transition function. But otherwise, we like if it does diverge, we don't want it to affect our cluster. So that's the standby. And the second reason is that this is going to be part of our reconfiguration. So when you like want to change the set of members of a cluster, you actually need to do two operations. One, you need to add replicas to the network and let them catch up with the state. And then you need to kind of like logically switch the set of replicas who process prepares. So this standby allows us to solve these two problems separately. Like we first add standbys, the standbys synchronize, and then we change some of the standbys into the primary. Anyway, yeah, so that's kind of like this column. And this column is just a visual representation of a replica's state and ID. So like this is the 0th column, and the 0th replica is here. The first replica is the next column. This one is the second, third one. Where is the third one? Yeah, this is the third and fourth, etc., etc. And the symbol here might be dot, which means that the replica is normal. It might be, actually, where is it in the code? See. Oh. Yeah, so dot means normal, then hash means that the replica is crashed. Actually, no. Oh, no. This one. So normal is dot. Crash, I think, yeah. Crash would be hash. View change would be v. Recovering would be r, and recovering hat would be h. Oh yeah. Coming back to this thing, you see, yeah, this is kind of like, wow, this is molarity. So here you see that. Where's my cursor? Okay. Here you see how view change happens. So replicas, like everything goes normal, then like something bad happens, someone crashes, and replicas try to change. So they start to change in view 339, and then they go all up to like view 345, where we actually like select a new primary and continue processing transactions. Okay. So yeah, as you see, running our seed for a longer time actually showed us a crash. And this is actually a different crash, and not a crash which we're trying to investigate, or because I've already seen this. So recently we added like write ahead log, which just like streams all the events to disk just for disaster recovery. And in our simulator, the write ahead log, append only file, sorry. Append only file for disaster recovery. And in our Whopper simulator, append only file is sized to some amount of megabytes to allow for like 50 million sticks with those probabilities of failure which we had, but we actually increase the amount of probability, so we just like run out of this space for that only 5. That's not really a really interesting failure. And actually, yeah, let's go back to this seed. So yeah, let's say we found this seed. How do we reproduce it? Well, we just go and run the simulation passing the seed as an argument. And actually, yeah, before we go, yeah, let's just notice that when you run a simulator, the first thing is that it prints you the actual seed. And for some failures, the seed will also be printed on when the simulator ends, but that is only the case if we kind of like maybe detect a failure. If someone like sigfold it or something like that, then the seed won't get printed, so we need to pay attention to the start to the output. Yeah, and then it prints like the actual configuration, runner configuration, which generated for this run. So you see that there's like 5 replicas, 2 standbys, 6 clients, and like some amount of probabilities, which is sometimes important. So anyway, when you run Whopper in this node with a seed, 2 things have besides just producing the seed, of course. First is that this node by default runs Whopper in debug mode. So again, in our build.zig, we have like some fancy logic which says, hey, if you don't pass the seed, then you probably want to run us in a loop and want to like found a better seed. So we're going to compile into release. But if you actually do pass the seed, well, then probably you are trying to reproduce this failure. So we're going to be helpful and compile this thing in debug. And the second difference is that this produces a lot more of login output. And that's, again, kind of like half the thing which simulator tries to do for us. So again, usually this is helpful. Sometimes this is not. So it's might be useful to take a look where this logic actually happens so that you can disable this. So
Alexei, did it crash in that run, or did you terminate it in the most recent run? Did it crash, or did you terminate it right now?
No, it crashed. It crashed with an assertion error, which we will get to soon. Okay, so this is our build.zig file, and here you see that we should be able. This is like a strict that okay, if there is no arguments, then we build in release. Otherwise, we build in debug or whatever. And login is controlled in the simulator itself. So there is like some fancy login configuration at the start of the file. And also there is like this log function in the end of the file. So if you're like trying to print something and it doesn't get printed, then it's probably our smart filtering it away.
Yeah.
And sometimes it is useful to use less chatty version, even if you produce a failure, and that is like dissimulator log equals short build flag gets you. So you see that this is just.
And is this still in debug with the short flag?
Yes, it is still in debug in the short flag, and there is like the release save equals true or something like that if you want to like change the debug mode. So basically, you can control both login and build mode from the command line, but there is like I'm trying to do what you mean logic there as well. Okay. One thing I guess I want to note here is that login is somewhat chatty and somewhat verbose. So let's actually try to see the difference between full log and the short log. And I think I want this to be full Whopper and short buffer. And by the way, DJ somewhere has like Vim syntax highlighting for the format of our log output. So kind of like if you look at those logs often and for a long time, it might make sense to just like, write proper syntax support. But I didn't yet do that for this code though. So that means that I haven't. Okay, so. Yeah, you see that full login took somewhat longer. I'm actually quite surprised that they are like usually there is like 2x difference between the two, and here there isn't just like 30%. Maybe because everything is slow because of the streaming.
Is it because we're running it with short, so it's not actually giving the debug logs, even though we telling it to redirecting it to a file, but we're only redirecting the options, but not all the debug logs.
That's actually okay.
I think we captured that with short on the right hand side. That's it. Simulator log equals short.
And the other one says simulator log equals full, so they should be different. But actual files are, well, yeah, that's okay. I was also confused by the size of the file because it's like 1.3 something. So I was assuming that they are kind of like the same thing, but actually you see that. Oh my god, I can't see the cursor. One is 100 kilobytes and one is 100 megabytes. So yeah, there is a sizable difference here. Okay, so let's actually get to debugging the thing. And for that, first of all, I actually show you my actual workflow. And yeah, I'm kind of like an engineer who doesn't know Vim. I know Vim, but I don't use it. I use VS Code. So I don't drive this thing from a terminal. I drive this thing from my editor. And I have this like short TypeScript Dino program, which allows me to like quickly run the simulator, quickly run the specific tests, like run simulating release, like run the whole cluster of like real TigerBeetles, like not a simulator, but real cluster. Like, anyway, so that's kind of like, kind of useful. And actually, I want to probably going to say the shortcut here. Otherwise, like we'll be waiting for it forever. Okay, and while we're doing this, let me actually show the code which actually failed, because that's interesting. This is going to be in our checker. Okay. So what fails is this assertion. And this assertion isn't inside our replica. This assertion is in our state checker. What is a state checker? So again, when we run the simulator, when we run a cluster of TigerBeetles, we want to observe like certain properties of a global state of the system. Namely that like everything is linearizable, everything is durable, like if you commit something, you cannot have committed, whatever. And while we have a whole bunch of assertions inside our replicas, and those assertions catch a lot of potential problems, an assertion inside the replica cannot check the cluster-wide state of things. And for this reason, we have this extra state checker. So state checker is called for every replica. And it observes the state transitions, which cluster as a whole is doing, and does some extra assertions there. And this is the assertion I added earlier this week. And this assertion is fake. So either means that this assertion is actually good and found some curious bug we had, or that this assertion is buggy and it needs to be adjusted. So what is the idea here? Basically, you can think about, well, there's like two ideas here. First of all, is that when replicas participate in a cluster, they make promises. Like when a replica accepts a prepare and replies to a prepare awk, it makes a promise. It actually makes two promises. First of all, it promises the durability of the prepare. It promises that, hey, I have written this to this, and with high probability, I will actually be able to return this. Again, replicas do not promise like 100% durability because this may fail and replica might actually not be able to recover prepare it accepted. But we make an assumption that enough replicas in the cluster actually have this prepare on this okay and can recover it in the future if some replicas get this prepare corrupted. The second promise which replica makes when it applies to prepare off is that it is not going to accept any different prepare for this slot in the current view. So again, in view stamp, like basically, when we do replicating state machines, we want to like converge on a linear sequence of events, on a linear sequence of prepare. That turns out slightly different. Do this linearly, and that's why you tag each prepare, each iteration with two separate numbers. You tag it with an iteration number, which is like what you would think an iteration number is, just like the linear sequence from the root. And you also tag it with a view number. And it might actually be the case that during the iteration of the cluster, for a single op number, you have different prepares. But those prepares must be for different views. And there is also a certain view number ordering rule. Basically, that for a given slot, a prepare with a higher view number wins. So this is exactly the invariant which I'm trying to check here. So when Replica runs, it has op, which is also sometimes called the head op. This is like roughly the highest prepare this replica knows about. And replica also has a view which tells which view this replica is in. And like roughly, this view of tuple needs to be graphically increasing over the lifetime of the replica, including restarts. One complication here is that, as I've said, this is not actually true, because what might happen here, because what happens here is that replica updates op, this number, even before it durably persisted with prepare. So what might happen is that replica accepts prepare, it bounces the op, it schedules the prepare to be written to disk, it sort of crashes, it restarts, and it will actually be able to like truncate the op and go back, because it didn't actually tell anyone that the op is durable, so it's okay to pretend that it didn't actually receive it. So what we actually do in the state checker is that we see every prepare op message sent by the replica. And we remember kind of like the biggest operation in terms of view of tuple ordering, lexicographic ordering, which this replica promised to like guarantee. So we like for each replica, we remember it's like highest view and highest op, and update it on prepare ops. And then on every tick, and yeah, this is actually interesting. So Let me see where we actually call this check state. It happens in the cluster. Yeah. On every prepare of send, we update the replica head, and on every tick, we check that replica head didn't backtrack. And if you see in the replica, there is this actually in the actual replica, we have this on message send hook, which we call right before we emit the message to the network. Okay, so this like roughly explains what happens here. Let's see if we can. Let's start debugging this basically. I kind of like explained to you everything I know, so now you know as much as I know, and you like have zero excuse of not actually being able to debug this. So let's do it. Okay, so we see that okay, my cluster is like trying to commit something. Cluster tries to do a view change for some reason, and then someone fails. Again, I guess there are three ways to how you can debug this. One is you can like look at this like 100 megs of logs and use like grep and like look at the logs and understand what's going on there. But this is not a workflow I'm like super proficient with. Like I mean, I like try to grab stuff, but yeah, I also kind of like find out that like actually like adding printfs and whatever works better for me.
That if I can add, that's what I used to do. So I would just output it to a big file, and then I would grep. If it was, I would sort of start to subdivide the space and see. I would grep for like view changes, any function prefixes, grep for those that indicate a view change is happening, and then try to see, are we doing lots and lots of view changes? Because that could be something around our view change protocol or repair protocol. Or are we not doing too many view changes? Okay, maybe it's something else. Maybe it's like some message that's corrupted, and then I would like search for that checksum and grep the logs for the checksum. But eventually you can pipe and use lots of greps together, and you can use grep to exclude some keywords to like narrow your logs down. And that's what I used to do. So I'm glad, Alexi, that you don't do that. Now we can see something different, right?
Yeah. Like I mean, like I'm so bad at it that I don't even like know how you like go to the end in less. Like, what's a shortcut to get to like the end of the file?
Yeah,
It's shift colon G, shift G, basically capital G, I think.
Okay. Okay, so you're already better at this than me. Okay, yeah. So yeah, you see that. Yeah. So what happened is that like someone crashed. Someone tries to recover something, and presumably then this same thing actually crashes.
Zero replica zero crashes, right?
I think so. So let's actually like try to do this my way and like add stupid debug prints to see who's actually to blame. So we probably want to see a bunch of things here. Thanks. So we want to see replica. We want to see replica view, replica up, and we want to see
By the way, Fed chimes in with a comment that you can also press the end key to jump to the end of the file.
Okay, that's actually.
Does it work?
That's actually. Oh, let's see. Okay, yeah, it works. Home and perfect. Thank you. Okay, because we already have Replica here. And let's see if that log actually gets printed. Yeah, so yeah, the second approach is like to do what I'm doing, like just like stupid like printf debugging, like you're a caveman. And the third approach, which is kind of like I think how one should actually debug those issues, but which I haven't like mastered yet, is how do you call it? Like our thing, like time travel debugging, where you basically kind of like record the trace of the whole execution, load it into your debugger, and then you like step forward and step backwards and see like what actually happens there. Like that's like I mean that sounds like a very fancy and cool approach in theory, but I mean like I don't have a great debugger. Like debuggers are horrible. Like I don't do command line. I don't want like a terminal debugger. I want like a debugger like which like I know like actually works. Okay. Yeah, and here we kind of like go to like this interesting bit which I was like telling you about like smart plugin is that by default plugin is smart, so you can add extra login and actually don't see this in the output because in our simulator we basically filter out everything. So let's say that yeah, we actually want full log and I know that clocks are chatty, so like I just want to manually shut down everything from the clocks. Okay, I think I don't need because we are setting up the short log. And we also have like this extra level of login. So I want cluster to be info and replica to be debug. And it's interesting that I don't actually know who our state checker is. Okay, so it's state checker. Let's say that. Anyway, this is all reproducible. So you actually can go check this commit, check the seed, and try to debug this at home, and you will be seeing exactly the same results as I am seeing. And tell me, hey, Alexei, this is like actually easy, and you're stupid, and why are you wasting so much time debugging this? Oh, okay. You can see what happens. Yeah, it's like from logs, it seems like a zero replica crashed, and then it recovers, and then it tries to start a view change, so it sends the view change, and then we do the tick and catch that it actually. Okay, now everything is debugged for some reason. Okay, because yeah. Actually want everything to be in debug. So yeah, like usually when I'm doing printf debugging, I debug through logs, but I also set the log level just to error so that I can like get rid of all not that interesting stuff. and perhaps like not the most efficient workflow.
Just to double check, we know it's an index out of bounds, but I don't know if I've missed it. But
no. It's not index out of bounds. It's an assertion. Index out of bounds was that like previous wrong failure about an of the file.
Okay. So we still like, I don't know. Any guesses like how close we are?
Why? There's too many outputs here. Okay, because I also want this to be error. Yeah, so yeah, kind of like it's like
Replica view head.
so yeah. So while I'm probably not, let's think what is happening here. So we basically like forget about one iteration. Hopefully we will get a printf I'm at it, and we will actually see what iteration we missed. And then presumably we can grab for logs for this iteration and see why did we not, why did we like roll back our promise error.
So Alexi, if I understand correctly, we're realizing that the replica's view is behind the view in the log suffix, the head view. Head. Can you?
That's okay. So that's actually interesting. So we jumped straight into view change. And that means that we actually shouldn't be hitting this assert at all, I think. Okay, yeah, so this is just like printout. Printout tells us that like replica's view is 65, and replica of is 69. While sometime before, this replica actually has signed a prepare op view 65 and op number 72. Which, like, yeah, kind of like, right now it does sound like a bug. And actually, one quick thing to check would be, yeah, so we have like 5 replicas. So it's not like we have some like extra logic about like 2 replicas or 1 replica where we kind of like do something fancy with preparers, but for 5 replica, it should be like pretty much normal case.
And it's not, could it be something in the standbys, or the standbys are excluded from this check here?
I think actually that's okay. The standbys are not specifically excluded, but they are de facto excluded because they don't send prepare op. So they don't make promises, and that is just like for standbys it should just work naturally. And we see that replica 0 is not a standby. Well, first of all, because it's like replica 0, so standby numbers of standbys are also like higher. Yes. And replica 0 is like a single replica for which you can be sure that it's like definitely not a standby. So we are lucky here. And yeah, we see that it actually sent some commitments. Okay, so but this is actually interesting. So we actually like truncated a fair chunk of like 70, 71, 73. We like truncated free prepares somehow during restart. So let's.
So it acknowledged up to 72 before, but the last log is for 69. Is that the issue? So it's send
Yeah.
a prepare. Oh, okay.
Yeah, so we acknowledge up to 72, and then somehow we rolled back to 69.
Hmm.
And I think that happened after repair, after restart. And we actually, let's maybe just like grab what happens with like the first iteration, which we erroneously truncated up 70. And I think we also want to grab for zero replica, so I think something like this should. Okay, so here is everything which happens with op number 70 using zero replica.
So it becomes primary at some point as well, zero after doing the repair. Because it says
So,
start view as the new primary. Does it mean that zero is the next primary? Or
yes, it
okay.
started. It started to use a new primary. Okay,
Hmm.
that's okay. So actually, yeah. The story of the separation is interesting because Okay, we
Okay.
are.
And we're back. Alexi,
Yes.
great,
Okay.
cool.
Okay, Alexi, I think I want to understand what you were saying before we dropped. So
Yeah,
so
yeah. So
basically
let's
what
try
what
to.
okay,
Chaitanya, let's
yeah.
actually like try to repeat this because I think that that people dropped on the most interesting place in the stream.
Sounds good.
So
Sounds good.
yeah, I think I have a hypothesis what might be happening here. So again, if we look at our logs for op 70, uh, we see that yeah, we see that we actually send this prepare awk after we like become a primary. So and when replica becomes a primary, it kind of like sends prepare awks for all the prepares it has. And I think it also sends these prepares to oneself. So my hypothesis is that kind of like we updated this like maximal head when we were sending prepare to ourselves as a primary. And that I think actually is the case where it might be okay for us to roll our promise back. Because again, we haven't sent anything through the network, so it might actually be okay for us to truncate this. Now, we can see this like in this code. So this is the code for sending a message. And here we send the message. But if it so happens that we want to send a message to ourselves, then, well, we don't send it through a network, we add it to loopback queue, where like loopback queue is like actually just like nullable message, nullable field on the replica itself. So, okay, my hypothesis is that so we are sending this message to ourselves. Let's check this.
This makes me feel so much better, Alexi, that you also do printf debugging. Yeah.
I guess I have like very experience that once like like static analysis based IDEs actually work correctly, I should like do some debuggers because I really like I
Yeah.
mean like the reason why I do printf debugging is that before like going to Rust and Zig, I was like working with Java, and like debuggers in Java are so awesome and like light years ahead of what GDB or LDB gives you, that I kind of like don't like feel that like like I mean yeah, anyway.
Yeah.
Debuggers needs to be better. Let's keep it short. Yeah, and that's and yeah, and the problem with printf debugging is that because we don't actually we should implement minimization, like really. Like I feel like if like for these 7 hours I actually let like our code to run and try to like minimize this bug, like we would like debug this like already by this point.
Yes, definitely. Did we already check that for the given replica we've identified any duplicate log lines for the same view? Because maybe we might see for the same view like 65 or something that it has op 73 and then it regresses later.
Okay, so yeah, it is my prints and they're kind of like useless, which is like okay because I try to make this less verbose, but inverted the condition. So I actually print this every time I don't need this to be printed, which is not useful. Okay, and this log also wasn't like super helpful. So let's actually see that if message and I want to print. So you want to grab logs for duplicate what?
I was just wondering if we had checked it for the given replica, if we can see all the logs where the view is 65, and maybe we'll see that the op regresses. If it, like your theory that maybe it's getting a stale message.
So, okay, so we want to see for 65 view for 0 replica.
That's it. Yeah.
Here is a bunch of. I'm trying to, like, in parallel, do printf debugging and like log grephen.
Yeah. How are you feeling that side, Alexi? Are you good, or are you getting tired?
I'm good. It's actually even in Portugal, so the temperature is much lower.
Okay.
It's actually better than it was like in the middle of the day. So I'm inspired.
Okay. It's
But
the
you know,
code.
like it's like four stages of grief haven't started for me yet.
Okay, good. Yeah, I'm similar time to you. It's the coding hour. So
Yeah. Okay. Does anyone know how to disable soft wrapping in less? Or like enable, like basically I want to see like a line on a single line rather than these things like wrapping around.
Sure about that.
It's kind of
yeah,
like hard to see what's going on with view 65 here. Okay, I know, I kind of like.
you could also chain the RGs and pipe them up to further restrict them.
Yeah, I also can like, open this in graphical editor,
Yeah,
which has soft wrapping.
Yeah.
there we go.
So what has been happening with like view 65? Waiting for quorum. Yeah, so Replica 65 tries to do a view change. It's waiting for quorum. It gets the quorum, and it tries to do the change. Okay, this is okay. So this slide is actually interesting. I wonder where it originates from. Let's go back to Replica. I want to understand what's the meaning of like this op ranges and commit ranges, because it feels super relevant to what we're doing here.
It's exactly the operations that we lost, right? 69 to 7, yeah, 70, 71, 72.
Yeah, that says like that. And I cannot actually end it. Okay, let me do this way. Okay, so that is that line. Okay, so this is like set opens commits max.
Previous commit max. Commit max.
Yeah. So this is truncated iterations. Okay. So let's see what's our printout there was. I forgot. Okay, so my hypothesis. Okay, yeah, actually, we do have this. Okay, I guess I also need to. We do have like this send to self equals true printout, which I expected to see, but actually didn't check that iteration is 70, which is what I want to see.
Mm. I'm looking up to the roof for inspiration. Do you think it could be the Vopper change, Alexi, where maybe it's injecting more faults, but even then we would just be unavailable, we wouldn't truncate.
I feel like I kind of like sort of understand what's going on here. So it seems like that's like just the bug in that assertion, because like Replica decides to be a primary, and like Replica decides to truncate messages, and after truncation, we hit this assertion because we sent prepare rope in our new view. So yeah, I think what's happening is like some interaction with prepare or whatnot. So basically, like the primary transitions to view change for this new view, it kind of like sends a message to itself that it has prepared doc this header, and then it gets like the view change log, and it actually decides, okay, no, I'm going to truncate this. And that presumably is okay because, well, it was a message to itself, so it doesn't matter. It's primary. It decided like primary can change its mind as long as it doesn't tell about this to anyone else.
But Alexei, weren't those committed entries, 70, 71, and 72, or were they not committed?
They were not committed. If we look here, like our commit is like just
Okay.
68, 57. Okay, I guess
It is possible that it could have been committed on the primary that crashed. But then what will happen now, the new primary isn't going to truncate the log suffix unless it gets NACs from all the active backups in the view change. They're going to say, no, enough of us didn't prepare that operation, so we know for sure that the old primary couldn't have committed it, so it's safe to truncate the log.
I think that's actually what happens.
Yeah. Yes. Yeah.
Do we have some log tells us like, hey, we knocked this.
Yeah, we could search for like some of the checksums of these messages. I don't know, and see if we're seeing knacks for them or commits for them. Because if a replica commits an operation, you will see that checksum show up in the log. So some of these knacked operations, we could just double check and see, like for example, op 69 or 70, we could just search for that checksum, see did the old primary actually commit it through the state machine before crashing. Then if we don't see that, then we know for sure that the new primary is safe to truncate.
Although I think, yeah, I think like this log line actually kind of like pretty much tells us that, hey, all those ops were truncated.
Yeah. It is possible that 69 could have been committed by the old primary because that knowledge wouldn't yet have propagated to the rest of the cluster. So the commit numbers we see here for 68, it is possible that 69 through 72 could have been committed. So that we need to look at the knacks to be sure, which is what the new primary will do.
Yeah, well, and it did that.
Yes,
and it rolled back from 72 to 69.
Yes.
So we do have knacks for 70, 71, 72.
Yes. But what I meant more was that we could look for the earliest rolled back op. We could look for that op number to see if it was ever committed, just to double check. And then we know like the old primary never committed that op. And then we know it's just a bad assertion in the Whopper. Is that like just to double check? So we know that this is kind of interesting for you, Chaitanya, as well, is because what you're seeing here is the control protocol from protocol-aware recovery. So we're actually able to provide higher availability because we realize, look, some of the ops in the log suffix were corrupted and we can't recover them, but we can be sure they were never committed, so it's safe to truncate them.
So we can truncate.
And then the cluster can remain available, whereas normally Raft or normal VSR would not have been able to remain available. So we could, Alexi, does it, do you follow what I'm thinking? We could sort of just double check, like look for op 69 and just check that there was no entry in the logs on any replica that it was ever committed in the state machine.
Okay, so what should we grab for?
Just op equals 69. And just to see if we see it committed, because if I recall correctly, we still, every time we commit an op through a state machine anywhere, we log that in the debug logs. We could sort of just grep for anything showing we're committing an op, and then we could further refine that.
Yeah, I know. 69 doesn't seem committed, and actually that's...
Yeah. It might be, we could search also using the function prefix, like commit colon.
So actually
if it is still that.
So okay, wait. So I'm looking at prepare ops for op69, and I see prepare ops from all the replicas, which doesn't make a lot of sense to me because we have two standbys. But I think that's because, well, standbys kind of like pretend to send prepare ops and like don't actually send them at the very end. So okay, op 79 isn't committed. Is committed probably because, well, we have prepare ops.
Yeah.
Oh, it's actually.
Although
Okay,
it could be that they were sent but never received.
But
So we could
I mean,
still, to be sure, we could just grab the log for where we see it being applied to any replica state machine where it does a state transition and see do we
okay,
see.
let's. Okay, so
That's it.
this
Yeah.
should be commit dispatch.
Awesome. I've learned a new trick with piping to unique, by the way, and sort. Like I've never done that before with all my gripping, you know.
Okay, because I'm not looking for an op, I'm looking for commit main. Okay. Actually, I guess I can grab just for commit main.
Yeah.
Because that's exactly what we are looking for.
Mm-hmm. So 69 didn't get committed then.
Yeah, well, I mean, it didn't get committed locally on every replica, but it might have committed by like faster because again, op gets committed once we have a quorum of prepare ops somewhere. Okay. So anyway, I'm like super confused by these logins in here because
We didn't see 69 dispatched though, did we? Did we? I
No,
think the
we
last
didn't.
didn't. Only 68.
Yeah, only 68.
Okay.
But
yeah,
Alexei, if a majority of replicas did act for 69, there should be some logs related to that, right? That we did get a quorum for that, or like some.
we actually this is it. So
Oh, okay,
Although
this was
this,
specific.
got it.
if I understand correctly, this doesn't mean we got a quorum. It just meant that Replica sent the message, but the message might have been dropped by the network.
Well, this is infuriating. So basically, kind of like when we send a message, we kind of like send it, but then we have a bunch of last minute checks before we actually send that message. Like we can say, hey, I'm sending a message, but then at the last minute, if your view is not durably updated, or if you're a standby, you are not actually sending this. So if we actually did send those messages, even if network dropped those, we still committed because well, if we send message, we kind of committed to our locally accepting to prepare. So we made our promise and etc. etc. But if we actually,
what I mean, just to clarify, is the primary wouldn't commit it until it receives the messages.
we might not know that it is committed.
Yeah, but in the next view, those if a quorum have the operation, it will survive into the next view. Then it will be committed later. But so I was referring to just the primary wouldn't commit until the messages are actually received. So I was just wondering, did we do the commitment dispatch for 69? Or did we only do it for 68?
So for 68, we kind of like get it.
Okay.
And for 69, we don't get it.
Okay,
because
thanks.
69 is not committed locally by any replica, and also
okay.
cool. Pax is also
Okay, so, well that's perfect.
Hey Alexei, what about just curious, what about 70? Were there any prepare OKs for how many prepare OKs did we get for 70?
We get a bunch of those.
But not enough for quorum.
That actually is not clear. So we have 5 replicas, so 3 prepare rocks should be okay. So like again, this is what I find infuriating. Like this self prepare rock doesn't mean that we actually send it. It doesn't that doesn't signify commitments. You probably should like add some extra log there or something.
But it does mean that the op is durable in the log for 3 out of 5 replicas, right?
Yes.
Is there?
Yes.
Except for maybe what Alexei mentioned, the caveat. If like some of these are standbys, then
Oh,
Yeah.
okay.
But
So they won't participate in view change. If they're standbys, they won't participate in view change, right?
So replicas 5 and 6 are standbys. Everything less
Okay.
than 5 is actual replica, and we here we see prepare rocks from actual replicas.
Oh, so
So we see for 71 and for 72, like you should see, yeah. And you see this is cool. Out of order prepare, so we get more prepares for op 72 than for op 71. So
this is also
so is
showing
it?
us how pipelining works, because we can replicate multiple ops in the log and pipeline them to prepare them out of order even. But then what one could also do is look at the on message handler and see for the primary, is it receiving these messages? And we could look at quorum like that. There's 2 quorums, like in the current view, what does the primary receive? What is the primary thinking? And then in the next view, what would survive into that view or that way? Yeah. But it looks like, if I understand correctly, we're safe because the new primary is truncating the log and it's truncating operations that were never committed. Yeah.
Yes. I think we are safe, and I think that the bug is like in our checkend. But I want to like still understand why is the case. And so what bugs me is what I'm seeing on the screen right now. So you see, we transitioning to the view 65. So the view 65 is actually the like very new view. There wasn't this view before, and we also the primary for view 65. And somehow we actually get a prepare log in our log, which is already for review 65 and for higher iteration, which like makes 0 sense to me. If you see what I mean. So basically kind of like we like in our like assertion here, we said, hey, kind of like our like basically we backtracked before the max, and we compare views before we compare iterations. But this view which have just started, how could we like prepare rock something in that view?
Could it be that we did the view change, then we crashed, and then we recovered our log, and it could be maybe that the new primary did the view change, truncated its in-memory journal, then crashed, and then came back up, and then I don't know, and then sort of rejoins the view, but then it sees on disk that it's got higher ops than, or maybe it is some, yeah, basically it has the ops locally, decides to truncate them, but then realizes like what it has durably is different. Maybe it is a real, there is something there. It's not a correctness bug, but it's still a bug because what we're doing in memory in terms of truncating is not, we're not doing the same on disk. That's a hypothesis.
I'm kind of still confused. How can we promise something for like view 65 and OP higher than 69 if we have just started this view?
That's what I was thinking. Maybe one explanation is that we've started the view, which we truncated, but we truncated the view in memory, and then we restart from what's durable on disk. We've made the view durable on disk, but maybe we didn't make the decision to truncate
To
the log,
truncate.
the op. We didn't. I'm not sure. I'm a bit distant, from the VSR state we make durable. So maybe at startup, then we start up and our head on disk is further, which is why we then send the prepare OK.
So I think that like this is also the view where we are the primary. And if we crash as a primary and recover, then we upgrade our view.
Yeah.
So what I did here is actually just like crashed at the moment where we are like saying this prepare. So let's see how it happens. Okay. So this is send prepare rocks after the view change. And what is actually our like actual view here? So this is like, okay, so this is like the view. Okay, so I guess I'm confused. So when we send the prepare has a view and an op. And then we send prepare rock. And the view in prepare rock might actually be different from the view in prepare. Yeah, obviously it has to be different.
Are you thinking that we're getting a prepare OK from ourselves from the previous view?
Okay.
Alexei, could you explain for us what the assertion checks? Just to reword it, what it is.
Yeah. So we had a history of iterations, and like each iteration is tagged by two numbers, view and op number. And we have like two invariants. That's first of all kind of like the global history is monotonic. There is no forks, but also that each local history on the replica is also monotonic. So if a replica is in a view, then kind of like it either appends to the current view or it truncates some suffix of a current view and switches to the new view. It cannot like say, hey, I truncated op 5, like my latest op in view X is 5, and then later it says, hey, actually, my latest view, my latest op in view X is op 3. Because if we ever do this, we actually would then erroneously stand next during view change, which is like the backstory for this change is that I found a bug in our view change protocol, which wasn't actually triggering by Whopper, and the problem there was exactly this. So kind of like replica like appends something to its log, then it restarts. After restart, it erroneously truncates the log. And this is problematic because then it can send a neg for this message, which would be wrong because previously it accepted this.
Yes, and then the specific assertion that fails, we compare it with head view. That's in the, okay.
Yeah.
This is where we sort of check the replica state. replica head max, and we say if the replica status is not recovering its log, then maybe is the state checker correct? How it updates replica head max? Does the state checker update the op also, like through a view change?
So I think that the stack trace we have here is actually very tenor. So this is like send prepare orgs after view change is when we send a prepare org for org 70. But by this point, we have actually truncated the source. So let's actually view 65. So if view is 65, let's log, what do we log? We log self replica, and it should be 0, just in case. We log self op, and right. If we actually do truncate, then okay, actually, how our NEC protocol works. So let's say I'm a primary, I have the full pipeline from a previous view. But then, I am becoming a new primary. I received a quorum of view changes, and I realized that hey, the whole pipeline should be truncated. Well, but actually, yeah. So yeah, basically, what happens if both of these are true? The prepare is truncated, and the primary actually has this prepare when it starts new view. What do we do here?
If I remember correctly, if we truncate the log suffix, we're careful to also update the primary's pipeline in memory accordingly. Yeah.
So basically, we just throw away the prepare completely.
And in the journal also.
Because okay, I kind of stop understanding what is happening here, because here we clearly say that we truncate our op to 70 to 69. But at the same time, we kind of send prepare op for op 70. But we shouldn't be doing this.
Well, Alexei, I was wondering, when we send the preparer K, are we sure that that's happening in the new view, or it's not? It's not possibly something delayed.
Well, we are sending this in the new view. We send it in. Okay. So
yeah, at the end, yeah, that as you showed in the stack trace, the send preparer case, to fill up the pipeline. Ah, okay. Over there. That's where we are. And that's what's sending it, hey? That's what we saw on the stack trace, as you showed us.
Yeah.
Yeah.
Okay. Okay, so I see two bits of conflicting information. First of all, when like primary starts to use a new primary, it sends prepare op for op72, and its actual op is 72. At the same time, we like truncated this op as we see in the logs. So those two don't add up to me. How do we where actual truncation happens? Like on do you change? Okay. Offhead, what do we do? Like where?
I didn't see the change where we move some of the NACs into the start view messages. So I'm not sure where we truncate now.
So I think I should be looking at this code right now. So here is like on do you change.
Yes.
We received a new do you change message. And we like added to our quorum and asked, hey, do we have a quorum of do you change messages so that we can determine our op head? And if we have the quorum, this op head is already truncated. So kind of like this is what we should truncate to. I don't quite see where we set our op, because okay, so here we actually okay. Okay, I'm blocking here because again I don't see like I mean this is that we determined the op we should truncate to, but where is the actual truncation code where we set our like self op? Okay, yeah, here it is. Primary is blocked from do you change messages, because here we probably do the same dance again. And somewhere here, yeah, so. Okay. So, oh, right. And this one is exactly, yeah, this is exactly the log we have here. So we set to op. Wait. Then I don't really understand this because
Could it be possible that we it's similar to what Joran said, that we set our op, but we could not perform the truncation on disk, and then uh, we we restart with the on disk state, and so we still have the op in our journal. Or is that not possible? Oh, you said that we increment the view when we come up, right? As soon as we come up, we increment
yeah,
our view
yeah.
if we are primary.
Actually, let's Do you remember how to print back trace, unstack trace? Here it is. How
No,
do you actually use this?
no, I haven't used that before.
Okay, I want to basically. Okay, let's see. Z print trace, web trace. I want to basically see two back traces where we have current stack trace. So I want to unseen max. And then here we basically will assert. One client here, so if you clearly see this.
Mm.
So yeah, so we. Okay, so this is zip, so I need to add some extra robustity, which is actually fine because, well, harder to try but easier to debug.
Yeah.
So again, this is like, this is useless stack traces.
Alexi?
Yeah, so in this, yeah.
Oh, I was wondering, have we got the full log with debug logs?
Yeah, it is
We've
right
got
here.
we've got that captured in a file. Could
Yeah.
could you lob it over to me on Discord chat, and then I can look around quickly on this side as well.
Let me try to do that. I wonder if it would be faster for you to just run this locally because it's like 100
Yeah.
megs of logs.
Yeah. Okay, that'll be faster. Okay, great. Let me do that. I just need to quickly. I'll get our Discord back. There we go. Let's do that. Okay. Cool. Thanks. Thanks.
Yeah, max file size is 25 megabytes.
Okay. Yeah. No, that's cool.
Yeah. Oh, right. You actually don't. Okay, so I was hopeful that like printing two stack traces will help me, but actually it doesn't help me because when we print the second stack trace, it is like it points inside Ticken simulator rather than some callback inside of a replica, which is
Yes.
like stupid.
Yeah. And where is it's in the PR, right? Where we've got the seed.
Let me, okay. So this one, I think I can send you over Discord.
Okay,
You
thanks.
want this commit?
Okay, thanks.
And you want?
And I need that little patch. It's
Yeah. You basically remove two zeros from each of the probabilities.
yeah,
The probability, like crash probability and like restart probability.
cool. Got it. So it's they both of them are 2, and then just without 1 0.
Without two zeros. Let me actually just like.
Okay.
Probability. Crash and restart probability should be like this.
Okay, let me check quick. Okay, replica crash probability is remove 2 zeros. Okay.
And the same for restart probability.
Okay, awesome. Thanks. I'm good.
Yeah. I guess kind of like if I'm trying to send someone to like reproduction, the best thing you can do is that you can like commit something and put a seed into the commit message. That's like bulletproof way to reproduce it. You just like check out the commit, run the seed,
Yeah.
like,
Yeah.
it's there.
That's brilliant.
Okay. Yeah, but yeah, it's oh interesting. So I have a hypothesis. We do update our view when we restart if you're a primary. But at the same time, like we might not necessarily like persisted our view to disk. So what could be is that we are in view 64, we restart our view durable at 64, we try to become a primary, we send a bunch of messages to ourselves,
Yes.
and we crash before we durably update our view. So we restart again, and we are again a primary. And this time we get a different do view change form, and we truncate different things.
Mm.
Okay, let me see this in the logs because I think.
Yeah. I've got something pretty cool to show you too. Let me see here if I'm correct. Well, let's do. Okay, wait. You carry on. Sorry, let me get this ready. Okay.
Actually, okay.
Cool.
What if we. what's interesting here is that we get printout that we receive the quorum, and then somehow we are waiting for quorum again.
Oh, okay.
So this probably is pointing at that restart thing. And what I have added right now, I added nonce to the printout, and the nonce so the problem with our logs, we don't know which section of the replica it is. We don't know if this is from the same section of the replica or if there was a restart between them. I guess you can see this. I guess okay. And actually, what do we do when we crash replica? Some easy printout here, which I can grab for.
While you do that, I just want to show I've got the same. Well, okay, wait a second. Does it share? Yeah, it does. Okay, cool. So I've got it reproducing on this side as well. And I was a bit rusty, but there it is. You can't see it on your side, but on Twitch, people can see it. And there. Let me do. I'm quickly going to do. Yeah, I could share my screen, but basically, yeah, I'm getting the same thing. Just pretty cool that we can reproduce it so easily wherever we are. We just pop a seed. And I was rusty, so yeah.
Awesome.
So we don't log the crashes and restarts, Alexi?
We log them, and I actually right now found.
Okay.
Okay, yeah, bingo. That's exactly what happens.
There's a crash.
Yeah. Perfect.
Yep.
So this problem means that the fix is essentially to move this. Okay, where it was.
Can we double check what view it's in when it crashes? Oh, it's in 65, but the view is not durable, so it crashes and comes back in 64.
It comes back and actually.
So why is it's while it's waiting for the quorum for the first time, when exactly do we make the view durable? Why is it not durable throughout when it's waiting for the quorum?
So yeah, basically, so the backstory here is like this. Originally, we didn't do durable views at all because, well, in the SR paper, you don't actually need this. You can do this from memory. But I don't remember why, but we decided that we actually kind of want to do durable views. And the way we implemented this is that basically with a hack, elegant, but still kind of interesting. So we don't add specific weighting for views to become durable. Rather, when we send a message, we check if our view durable is up to date. And if it is not up to date, we drop a message on the floor, which is exactly like that kind of thing I was complaining about in Prepare Rock, that it's kind of it's sort of there. We log it, we sent the message, but we didn't actually send it.
It looks like our view is durable before the crash. It's at 65.
And we restart.
Yeah, I'm seeing this.
So it read this from the superblock. Okay. 60 log view.
This is when we recover the replica 0 at startup. And then we do this. I don't know if you can share it that side, Alexi.
Okay. I can actually grab this locally. So we have yeah. Actually, are you sure that this is for the correct replica? Because we don't
It's
print replica.
that last one that I sent you, 0, transition to view change status, view 65,
Yeah.
65, status recovering to view change. I think that shows, and that is just after the one that I sent you. So I'm pretty sure that the superblock opening is for that same replica. And it's just after we restart replica 0. So that where we install the working superblock, that comes just after restart replica 0. So it looks like, I think what it is it restarts with view 65, but now it's going to see its logical log when it reconstructs the in-memory logical log, then, or the journal, then it's going to see the newer ops. Yeah. So it's kind of, we could maybe drill a bit into, do you think it could be now? What are your thoughts, Alexi? What could it be?
Okay, so well, basically I have like two thoughts. Like the first thought is like, yeah, we kind of like restart, don't make view durable, and like those kinds of sites don't actually exist. Sounds reasonable to me. But you are saying that we actually like do persist this view, which is interesting because like again, if we persist this view and we restart, then we should upgrade this according to the logic in replica open.
Yes.
We should move to like view 66. So let's.
Yes. The bit from, if you look in your logs, if you just cut the full log and then look for, just from the tail of the log, you'll see even without grepping, and if we just work upwards, it's actually not far to get to installed working superblock, and you can just verify that it was replica 0 and that it installed the superblock, and then shortly after it crashes, just from the full log without grepping. If we just
grab with context.
Okay. Yeah, you could. If you
Yes, I need more context.
Yeah, you can do C instead of A. A will give you context after. C will give you. If you do C instead of A, then you'll get before and after. Yeah, that should be perfect. Yeah. And
so did we in fact make the view durable? Did we?
yeah,
For sure. Okay, so that's not the problem.
Yeah, there we are. Just the installed working superblock, we're recovering replica 0. And if you go up a bit before where we install the working superblock, you'll see synchronously it's all replica 0. And then, yeah, restart replica 0 there in the simulator.
Mm-hmm.
So it looks like
Okay.
it's coming back up. There is something interesting where the superblock is corrupt, one of the copies of the superblock.
Oh, invalid checks. Huh?
But
Yeah,
we're still,
the first.
yeah, we're still getting a quorum. So yeah, to answer your question, Chaitanya, it looks like 65 is durable. And now when we come back, the journal of in-memory headers that we will have will now include the operations that we've truncated. And now, like again, like Alexei was saying, how is it that we're joining the same view?
So there is an issue there in that we are supposed to come back with a bigger view, but we are not, right?
Exactly.
Right. Well, no. Okay, I see. So we transition to the Digger view only if our previous view was view normal. So if we didn't actually finish view change, and we didn't finish actually view change in this case, we transition to the single. Yeah. I guess I understand this. I guess I understand the failure that the bag is indeed in checker. So what happens is Replica gets into the new view, view 65. It sends prepare op before it actually writes the view to the disk. So we actually don't send this prepare op outside. It didn't happen. Then it writes prepare op to disk and crashes. Then we restart. And after we start to actually truncate that stuff and see that like we kind of like backpedaled on our commitment. But the commitment didn't happen because we weren't actually sending those prepare logs because our view is not durable.
I think I would differ on one point is that I think we actually truncate the log before we crash. Because we crash with view 65 durable. Maybe if we go upwards, we might see where the operations get discarded. Before the crash. Because when I look at my full logs, it's immediately after we restart in 65 that we then crash. We don't even do a view change or anything or truncate. We don't run the NAC protocol. We don't receive, unless maybe I've missed it, restart replica, then we open it up. We recover the log. And now I'm looking a bit closely to see we send do view changes. What is weird, Alexei, just before the panic, we send some do view changes from replica 0, but we send it to replica 1, 2, 3, and 4. Do you see that? Like, why is the primary sending do view changes and sending it to multiple replicas for the same view?
What? makes like zero sense.
Yeah.
Mm.
Because normally this is something that the other replicas should send to the primary.
Yeah.
All the DVCs should come to one replica. Here, one replica sending it to everybody else.
Maybe it's just like a mix up and it should be sending start to you. Because, well, like,
And it happens just after we have reset. Do you see reset 0 DV change messages?
okay. I think that actually makes sense. So,
Yeah.
like, we now have this start view do change protocol. Start view change, do change. So when you receive start view change, you wait for quorum of start view changes. When you receive do change, you like immediately bump your view. So I think this is what's happening. Like broadcast do change to everyone to tell, hey, kind of like to really start view change.
Isn't it that the DV change gets sent to the primary? But here it looks like it's being sent. No, don't we send a view change from the primary? Or have we changed that now? The primary sends out a DV change to others.
Yeah, I mean, yeah, as per the protocol, it does seem like do view change is supposed to go from to the primary, and the primary sends start view at the end, right?
That's that.
So,
We should do that, I think.
Yeah, we do broadcast do change messages. That is like exactly to make view change happen faster. So kind of like.
But then it should be broadcasting a view change. Sorry, a start view.
start view.
No. Start view is broadcasted. Start view is broadcasted when you finish view change.
Yes.
So you finish view change, you broadcast start view. When you want to start a view change, well, first you broadcast start view change. But once you receive a quorum of start view changes, you broadcast do view change. And the difference here is this: when a replica gets start view change, it doesn't necessarily immediately start view change, because this start view change might happen from a replica which is asymmetrically partitioned, and like the cluster should isolate that replica rather than trusting it to start view change.
Yes.
Oh,
However, once
yeah.
a replica receives do view change, it is sure that it really needs to immediately jump into higher view, because do view change means that someone else received a quorum or start to change.
Start view change, yeah.
So this
I think
actually makes sense.
The part that is confusing here is that normally the DV change is only allowed to be sent to the primary. It shouldn't be sent to other replicas. Like we're kind of repurposing it now to do that.
Yeah, that's true.
Which doesn't seem good. This is to solve the asymmetric partitions problem.
Yeah.
Yeah. Oh, it's fine. It's just it was confusing.
Yeah.
So this is
Yeah,
fine.
I guess we are sending it solely for a view jump. So we kind of we ignore it, but we do a view jump there.
Yeah, because we used to have an assertion that a DV change, the destination of it was view number mod cluster size. Yeah. Okay. So this one we've ruled out, then this is the... What's interesting is that it's still trying to start a view for 65 when that was the durable view.
because it is in a view change. So that is actually okay.
Okay. Cool. Yeah, I'm still catching up as well to understand the asymmetric partitions, which I remember we fixed.
So anyway, let me just quickly check the hypothesis that
Oh, Alexi, if you check the very last line of the logs, just before panic reached unreachable code, it's quite interesting because there you see what the replica has in its journal on disk.
so
Just before the stack trace, it's the very last line, the info on the cluster. There we go. Replica 0, 65 view, 59, 68, and there in the journal we've got 72. I guess we all know this, but
yeah,
I thought it's cool how you can see it there.
yeah. We got have started with that.
Mm.
Okay. Anyway, kind of like I guess what is left is just like look through. We need to verify that before Replica crashed in view 65, it indeed only sent repair hopes to itself.
Mm. Cool. Okay, so we want to see before the crash that it's sent to prepare OK.
I guess. How do we like? Okay, what would be like the right command to truncate our full log to just the interesting case, like when like before the crash. So like again, we have like okay, we don't necessarily have like two crashes.
Mm.
Well, okay, so one thing I just like checked is that if indeed I only invoke for callback when when we actually send a message to the replica to the outside world, then the test passes. So it is indeed the case that this was for self-sent messages.
Yeah.
I'm like still wondering if that is like if that is actually valid.
Selective duplicate says, I hope the bug's buggy enough for 4 engineers.
Yeah. I feel like you're like getting closer to Rafael's prediction.
Yeah.
At least that fix makes more sense to me. Yeah.
It's pretty cool. It's a lot of fun for a change to actually do this together, It's hard work, but yeah.
Although, don't.
I know there's someone on the team who's watching who knows the solution.
Okay, well, I guess let's take let's take a step back. I sort of feel that we like fixed this, and I'm like trying to understand like and yeah, the fix is like basically like this extra if here. But I'm like trying to understand like if this is actually correct. So first of all, yeah, we confirm that this is due to self messages, and we confirm that this is the case where a kind of like replica restart in the same view, and where replica starts at a view, sends some view changes, but didn't update durable log view, so didn't send prepare ops to other folks, and that is okay. I think I convinced myself that there isn't actually a bug here, and that like yeah, this if is a correct fix. Like, I understand what's happening here. Because yeah, kind of like, it's important to also like look at this extra condition here where we like actually don't send stuff out if our log view durable isn't updated. That I think is exactly what or maybe I don't understand this. So let me ask you this question. So okay, in this case, this is actually okay because we are sending message to ourselves. But what prevents us from sending this message to someone else? Okay. Okay, right. So we are the primary. So we only send prepare rock to ourselves in this case. We are not going to send prepare rocks to other primary because we are the primary, and that what makes it correct, I think.
Is it not that when we restart, if we're restarting into a view where we were the primary, should we not just do a view change to a higher view?
We do this, but the trick is in this present case we actually weren't the primary in this view. The view didn't start. I haven't started yet. So because the view starts once we persist log view durable to disk, and this didn't happen.
Didn't we persist 65 to disk?
That was view, but it is not log view. So log view is still 61.
Okay.
What's the difference between view, log view and view?
So view is view normal from the DSR paper. This is log view is a view where like replica actually like basically log view is the highest.
Alexi's
I
frozen
lost you.
for us.
Yeah, I lost you for a bit.
There you go. You back?
Okay, replica recovered.
Yep.
Log view is a view where
Can't hear Alexi now though.
can you hear me?
I can hear Alexi. Chaitanya, can you?
I can't hear Alexi.
Phil
Maybe
can
I
also
should
hear.
maybe I should rejoin.
Yeah, we'll see you
Maybe
now.
I should rejoin.
Yeah. Hey, Phil, you there still?
Okay, cool. I can't actually explain. I can't actually answer to Chaitanya question on Chaitanya joins.
Okay, I'm back.
Cool. The one part of the view number is what is the highest view that we have participated in? And once we finish participating in a view, we persist that to stable storage so that we never regress our involvement in a view. And the what is the other? It's a tricky part of the paper as well. Like we actually had it wrong for quite a long time. There's two views in the VSR paper. There's view and then there's view normal. The highest view in which the replica had a normal status is view normal. And that number can be behind the current view. So the cluster is wanting to do a view change, doesn't work, wants to do another view change, doesn't work, wants to do another view change, doesn't work. Okay, now it does a view. That is view, just view, like that's the view. It's the view of the active view. Log view is, it's the view where the replica had a normal status, which could be a few views behind. Yeah.
Got it.
Yeah.
And which one out of so log view is log view the normal view? The one.
Yeah, log view is view normal in the VSR paper.
View normal.
Yeah, it's it's kind of, so we struggled to find a name for this, and we didn't want to keep saying view normal, but yeah, it's basically it's the highest view for which the replica had some idea of where the log suffix was at. And what that means is that in subsequent higher view changes, a few replicas are going to participate, and they're going to all share their log and say, look, as at this normal view, I had this log, and someone else says, well, as at this normal view, I had this log, and someone says, well, as at this normal view, I had this log. And we're gonna pick the replicas that had the log of the highest views, because they have a better idea of what the cluster decided. So that's the difference. Yeah. Yeah. Cool.
So in this case, was the view was the normal view lagging, or was it not? Sorry,
So
yeah.
we were in a view change. So our log view was like the latest time where it was normal, and like our view was above that. So you see in the Discord message, like the log view is 61 and view is 65. And Replica 0 as a primary was about to start view 65 before it crashed.
There you go. Yeah.
And it was about to update its log view to 65, but that didn't actually get to this. Yeah. So it crashed and it will start again in view 65. So I think it's time to like compose commit message here, because I think that's like the correct fix here. So we only invoke this hook if we are not sending a message to ourselves. Yeah.
Okay. Stepping back for a second, where did the self? How was the self message a trigger for this again?
So Replica 0 received the view change forum, and it decided that, hey, I'm starting a view. So to start a view, it concurrently did two things. It updated its log view, which is like writing to disk, and it sent itself prepare logs for all prepares that it had. And sending prepare to itself happened before it actually updated view on disk. That's why we kind of like recorded that we sent this prepare to ourselves, but then we crashed, and when we restarted, we forget about that because, well, our log view wasn't updated, so this doesn't actually count.
So okay. Now are we are we persisting the log view only after we send those messages?
It's rather the other way around. So let's look again at this code. Yeah, here it is. Okay, so if we are sending a message to someone else, and this message is prepare log, and our log view durable is not up to date, then we are dropping this message on the floor.
I somehow can't see your stream at all. This is a bummer.
Okay, so I need to check. Can anyone else see my screen, because I was rejoining and maybe it's not working yet?
No,
Yeah.
I rejoined as well.
I
Maybe it's an issue on my side.
I can see it, Alexei. If you move your cursor or
Yeah.
scroll your window, just to double check that it's refreshing.
So I'm typing hello, Joran.
No.
Okay, no, we lost your
It's
screen.
frozen. Yeah.
Okay.
Yeah. Okay. Do you want to stop your screen share and then reshare?
Yes.
Great. Cool.
Don't show this message again.
So I closed my Slack because the CPU for some reason was going 100%. Maybe it's just as well because Phil says DJ had some hints for you all in Slack. At least everybody knows that we're like really sweating and really like we don't know the answer, you know. So cool.
Okay, is it better now?
Yep.
Okay.
Perfect.
Okay, so this is send message to replica. If we are sending a message to another replica, and we are sending a prepare log, and our view durable isn't actually up to date, so we updated our log view, and we scheduled it to be written on disk, but that write hasn't actually finished, then we drop the message on the floor.
Okay.
Is this the fix, Alexei?
And the fix, this is our current code.
Okay.
And the fix is here. So actually, this is state changes. So we just like move all message send from like always say this to only invoking this callbacks if we actually promise this to someone outside of our like computer. Fix false error.
Oh, so this goes back to that. Like, since you said that the self message isn't sent over the network at all, we don't invoke that callback at all for that.
Yeah.
Okay.
Let's call this A0. I think we use like A0 for the primary and like B1, B2 for secondaries. And like it's very likely that we actually like talking about zero replica row and like replica number 5 or whatever. Very convenient. Of the messages.
I think Alexei froze again for me.
Yeah.
Because you seems to be here.
Oh,
Okay.
yeah, you're back.
Back again.
And
Cool.
probably you don't see me typing now.
Yeah,
Or is my screen still white?
Screen is gone.
Okay, let me do this again. Normal update. Oh, actually, this bit, I'm not sure. Have we seen two DDC quorums in the log?
I don't remember checking that. If we saw two do view change quorums.
Okay.
We see waiting for quorum, 0 on DV change v65, waiting for quorum, and then panic.
65.
If we tail the log, literally just 2 lines before the stack trace, it's better to see it just tailing the log,
Okay.
because you see, I'll share it in Discord. This is the last bit that you'll see.
Yeah, I see. It seems that we actually started view 66.
Not yet. We're still, Replica 0 is still in 65. Well,
Yeah, I think one started.
yeah, it's
Yeah,
got a, okay. But Replica 0 receives a do view change, and it says it's waiting for quorum, and then it crashes the very next line. So it could be that it's receiving a prepare OK while it's in view change status, which it's allowed to do because it's primary.
I guess it's like it like okay. I wonder like what happens like. Okay, it's up now is. What's the op for Replica 0 after it restarts? So like before it crashed, the op was like 72 or something.
Yeah.
Right after
Yeah.
restart, what is the op?
It is, well, literally, if you tail the full log, just go to just above the stack trace where you see panic reached unreachable code. The line just before shows you its ops.
Actually, I don't think there is an op there, which is probably a problem in our debug prints.
Okay.
Do we actually have? Do we actually put an op there?
I'm quickly fixing our stream. We had a power cycle, so just a second. Okay.
Yeah, we actually don't print that pop in that line.
Okay.
Can we? Okay. I don't see any logs for an op. Okay, I guess this stream kind of like sort of exhausted me, so I probably will go into like write some commit message and come back to this tomorrow to like double check that this is exactly what comes with it. I feel like my brain is a mush.
Yeah.
And there is like actually the second thing I want to verify here, because like again, so backstory. Why we even have this check in the state checker? That is because we had a bug which wasn't caught by Whopper, and that's kind of like this is like so. Here we are debugging a seed, but there is like an opposite exercise where you know that there is a bug, but there is no seed, and you try to like fix a Whopper. So I was doing that.
Yeah.
And this extra check was needed to cut a particular bug. And I verified that the check actually did cut that bug. But now that we actually moved the check later, I need to recheck that the check still checks that other bug which it is supposed to catch, which might be problematic.
Yeah. Just to read the answer, DJ, I checked it out. He says half an hour ago. He says so. Replica 0 starts the view, begins making it durable, sends act to self. 0 crashes, 0 recovers. The view is durable. Log view is not. Since we crashed in DVC, we reused the DVC headers from the superblock. So 69 is our op head to answer that question. And then this is the bug that Alexei thought it was. We shouldn't call the message, shouldn't call back when sending to self. And then answering my question, DVC isn't just for the primary. We're using it to signal to other replicas also to send DVCs. Cool. So I think you got it, Alexei.
Okay.
Do you
Nice.
want to quickly do you want to quickly just do with that fix and then we rerun the seed?
Yes. Let me actually also like open the pull request, because like if there is no pull request, it didn't happen.
I have a question. How the view is durable but the log isn't? How is that possible?
Sorry, could you repeat the question?
And how comes the view be durable but the log not? The log wasn't durable, so as far as I understand, the recovery get that gap between the view
Yeah.
number that was durable and the log wasn't.
So we have two view numbers, view
Yeah.
and log view. And the flow is this. So we are like in some state. We decide to do a view change. We update our view in memory and keep our log view. Then we schedule our new view to be persistent. So it is persistent. Sometime later, in like maybe we updated our view many times without touching log view, but sometime later we decided, hey, actually it's time to us to like accept the primary and become a member of like this like new view. At that point, we set log view equal to our view and schedule persist in the log view. And like at some point later, like our view and log view are the same. So I guess the core answer here is that we update view when we transition to view change. And we update log view when we transition from view change. And like view change is exactly the gap between the two.
Yeah.
Okay, so now let's quickly rerun the seed. Again, we need to, and I now feel bad that I didn't actually create a proper baseline where I updated this. Okay.
The idea that we had to do commits that have the seed in them, you know, like that is awesome for future, you know.
Yeah. But it's also good if you actually follow your own good ideas, which I didn't.
And it's also good. It's also good that we call ourselves out, like you do. So
yeah. Okay, so ta-da! Like we running with our seed. Well, actually, I already did rerun this with our seed like before. Like you probably didn't notice, but like that was like all kind of like extra printouts there. So let's like do like a clean thing. Our proper commit there.
So I've got one more question. If this passes, then I've got a question for us.
Let's hope that it does.
Yeah.
So what's the question? Okay, it's passed.
Hey. So here's the
Good
question.
job, everyone.
Yeah, well done, everybody. Here's the question. Like this was all deterministic, and we could just replay and we could add in debug logs, and it still took 3 hours. But how long would it have taken if it wasn't deterministic and if we couldn't speed up time? Because like this test run was sort of half of a Vopper run. So to get to the bug, you know, we had to run about a third. So it's like it would take 10 minutes of normal runtime, but we could, you know, keep replaying it in like 10 seconds. So.
Also, I was able to send 128 megabytes of logs to Joran. I sent it to numbers because everything is deterministic.
Yeah. So we didn't even have to do the full log shipping. I had to just figure out how to use the Vopper again and get to the same baseline, and we were good. Yeah. So yeah, pretty cool. So we estimated an hour and a half, and we took 3 hours. So that's how to estimate debugging time with deterministic simulation. You estimate it in times 2, but it's still maybe hopefully 10 times faster. Or yeah.
Well, I think so too. Yeah.
Well, what's embarrassing, I think like my quality of assessment that this is actually an easy bug was true. So it's like, again, it's not a bug in our consensus, it's like simple bug in our like verification. And it's kind of like obvious. I mean, yes, like you shouldn't consider messages sent to yourself as like durable commitments.
And I guess we've got to also say like there's the Twitch factor. So if you're live streaming and fixing a consensus bug, it's
Yeah, you know, like the saying it goes, like 1 brain is good, but 4 brains is horrible.
Yeah. Never go to sea with 2 chronometers. Take 1 or 3. But someone asks, like, finally, someone says, out of curiosity, who's running this laptop? The background shows a painting of Bruges, if I'm not mistaken, of my home region. Any reason? Is it Bruges, Alexi?
Okay, I think it should be Hunters in the Snow by Peter Bruegel, the Elder, if you are talking about this.
Yeah, that's it. Yeah, Bruegel, the painter. Yeah.
Yeah.
So,
cool. The guy.
Awesome. Yeah, thanks everybody. Thanks for joining us. It was tough.
Yeah.
It was good. It was very good. Thank you so much, Alexi, for walking us through this.
Yeah. And I even learned how to grab things and like how to go to the end of the last file. That's like useful.
Invaluable.
Yeah.
Cool. And Rafael
Okay,
also,
thanks a
Cool,
lot.
guys.
yeah. Rafael, you've it was pretty interesting for you.
Of course, it was amazing. Thank you, Alex, so much. It was amazing.
Okay, and we're still on time for you, I think, for your estimate. So,
Yeah, sure.
great.
Expect.
Cool. Cheers, everybody. It's been awesome.
Cheers.
Yeah.
Thank you, everyone.
Yeah.
Cheers. Great.